Hey everyone, and warmly welcome to this explainer. I am so glad you're here today. Let me ask you a question right up front. What do you think is the absolute hardest part of physics? If you ask around, you'll probably get a huge range of answers. Some people will say Newton's laws, others might say thermodynamics, or maybe quantum mechanics. But you know what? Very few will say units. And yet, a shaky understanding of the invisible framework of units is quietly responsible for more calculation errors, more lost exam marks, and just more overall conceptual confusion than almost any other foundational gap. So today, we are going to fix that completely. Okay, let's take a quick look at our roadmap for today. We are going to start with the framework of physics, dive right into the 7 base units, and then see exactly how we build derived units from those. After that, we'll navigate some really common traps before wrapping up with a quick recap and a few practice questions to test your knowledge. Let's get started. Section 1. The framework of physics. Because here is the absolute truth. You simply cannot do physics without units. You could memorize every single formula in your textbook, but if you don't understand what units those quantities are actually expressed in, those formulas are completely hollow. So why does the SI system even exist? Well, I want you to imagine a world where every single laboratory uses different rulers and different clocks. Before the SI system, that was reality. Different countries used wildly incompatible measurement systems. We had the CGS system using centimeters, grams, and seconds, the FPS system using feet, pounds, and seconds, plus all sorts of regional standards. The result? Total global chaos. Science thrives on reproducibility. If two physicists in two different countries can't easily compare their measurements, progress just completely grinds to a halt. The International System of Units, or the SI system, stepped in and completely solved this global chaos. Formally established back in 1960, and actually significantly redefined recently in 2019, it tied everything to unbreakable, fixed constants of nature. It finally gave us one unified global standard. Let's move on to Section 2 and look at the core alphabet of physics, the 7 base units. Seriously, every other unit you'll use is built from these. Now this right here, this is the ultimate reference table. I want you to bookmark this in your mind. We have length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. Understanding what physical quantity each of these actually represents is exactly what separates a student who just memorizes facts from one who truly understands the physics. Let's break them down one by one. First up, the meter, our unit of length. Now, since 2019, the meter isn't just an arbitrary length. It is intentionally tied to a universal physical constant, the speed of light. It's formally defined as the exact distance light travels in a vacuum in 1/299,792,458 of a second. It's no longer based on some physical metal stick in a room, because physical objects degrade over time, but constants of nature, they never change. Next is the kilogram, the unit of mass, which honestly has the most fascinating history. For the longest time, until 2019 actually, it was defined by a literal piece of metal, a platinum iridium cylinder stored in a vault in France. But today, it's defined by fixing the value of a quantum mechanical number called the Planck constant. This is a massive deal, because it means any well-equipped lab anywhere in the world can now reproduce the exact mass of a kilogram without needing to weigh that one specific cylinder in France. Then we have time and electric current. The second is actually the most precise of all our base units. It's defined by exactly 9,192,631,770 radiation cycles of a cesium-133 atom. Those ultra-precise atomic clock cycles are literally what make your phone's GPS navigation work. And the ampere, that's defined by the elementary charge, basically representing a flow of about 6.24 quintillion electrons passing a single point every single second. Rounding out our 7, we have the Kelvin, the mole, and the candela. The Kelvin is for thermodynamic temperature, and crucially, its scale starts at absolute zero, the literal point where all thermal motion theoretically stops. The mole fixes Avogadro's constant, acting as the essential bridge between the microscopic world of atoms and the macroscopic world of grams that we can actually measure. And finally, the candela. This one measures luminous intensity and is uniquely defined based on human visual perception, specifically how sensitive our eyes are to green light. All right, Section 3, building the derived units. I want you to think about something real quick. If those 7 are the only base units, how on earth do we measure things like force or energy or pressure? Let's find out. This is where you really see the power and beauty of the SI system. Every single quantity in physics, no matter how complex it seems, can be completely expressed in terms of just those 7 base units. Look at how force, work, and pressure all pull directly from mass, time, and length. There are absolutely no new fundamental quantities introduced. It's like a perfectly self-contained puzzle. Let's actually walk through a simple derivation together, step by step, so you can see exactly how this works in practice. Step 1, we take the basic formula for force, which is mass times acceleration, F equals ma. Step 2, we just substitute in our base units. Mass is measured in kilograms, and acceleration is measured in meters per second squared. So that strictly translates to kilograms times meters per second squared. Step 3, instead of saying that mouthful every time, we just package that exact combination up and give it a new name, the Newton. And as you'll see, this exact logic builds across all of physics. Joules for energy, pascals for pressure, coulombs for charge, watts for power. They all break down the exact same way into combinations of kilograms, meters, seconds, and amperes. And here's a pro tip. Anytime an exam asks you to check an equation for dimensional consistency, this is the exact concept they're testing you on. Okay, section 4. Let's talk about the common mistakes and traps, because even the absolute best students slip up here. Let's look at the foundational errors that cost people major exam marks. All right, this is absolutely crucial. Do not treat the kilogram as a unit of weight. I know we do it in everyday life, but in physics, they are completely different. Mass is a measure of the raw quantity of matter expressed in kilograms. Weight is the actual gravitational pull on that mass, expressed in newtons. So, a 70-kilogram person has a mass of 70 kilograms, sure, but their weight is 70 times gravity, which is 9.8, giving them a weight of about 686 newtons. They are not interchangeable. Using kg for weight in an equation is a severe, guaranteed point-losing error. Here is another massive trap, confusing Celsius and Kelvin. Again, in everyday life, Celsius is totally fine for checking the weather. But in physics formulas, especially thermodynamics and the ideal gas law, PV equals nRT, you absolutely must use Kelvin. Why? Because Kelvin represents absolute temperature, with 0 being true 0. The conversion is easy. You just add 273.15 to your Celsius value. But if you accidentally plug a Celsius value into a formula that requires Kelvin, your answer will be completely wrong. Section 5. We have covered a lot of great ground today. Let's do a quick, clean recap of the framework we just built. So, to summarize, the SI system is not just some boring administrative chore. It is the globally reproducible language of science. There are exactly 7 independent base units, and they are now securely tied to unbreakable constants of nature. Every single other unit in physics is derived from those 7. And finally, using the correct units is literally the most vital step. If you accidentally substitute grams instead of kilograms into F equals ma, your answer is instantly off by a factor of 1,000. All right, section 6, practice questions. Time to test your understanding. Think about these questions based on what we just went over. Question 1, why was the kilogram redefined in 2019? Think back to that vault in France. Do you remember? The old physical piece of metal was problematic because its actual mass could change over time due to microscopic contamination or wear and tear. So, scientists tied it to the completely stable, unchanging Planck constant instead. Question 2. Is the candela actually used in physics or just everyday life? Got an answer in your head? It is definitely used in physics, specifically in the fields of optics and photometry. It's really cool because it measures luminous flux specifically weighted by human eye sensitivity. Final question. What is the main difference between the SI system and the CGS system? If you recall, the SI system uses the meter, kilogram, and second as its base, and it is the standard for modern global science. The older CGS system uses the centimeter, gram, and second, and while you might still see it in some very specialized fields, it's mostly a thing of the past. And that brings us to the end. Units truly are the language of the universe. By mastering these 7 base units, you now literally hold the keys to dimensionally decode any equation in classical and modern physics. So I'll leave you with this final thought. Armed with this completely universal framework, what will you measure next? Keep learning, keep practicing, and I will see you in the next explainer.